seminar. Today, we are very happy to have Professor Tariq Alkhalifah from Saudi Arabia joining us. Tariq was also my PhD advisor, so I'm thrilled to give an introduction to him. Tariq got his PhD degree from Colorado School of Mines in 1996, and then he worked as a postdoc at Stanford University. Now he's a professor at King Abdullah University of Science and Technology. So Tariq is well known for his work in on acoustic entropy, and in the last 10 years, he and his team contribute a lot of novel algorithms to full waveform invert. And now he's mainly focused on the machine learning and the combined machine learning with the geophysical method. So Tariq, please start when you are ready.
Oh, thank you very much, Jindang, and I'm delighted to be here. As I mentioned to Laurent, the last time I've been here was like not here. Of course, it turned out to be another building, and I cannot find records exactly when I was here, but about 25 years ago, either 97 or 98, 1998. And at the time, Nafi was heading this, and I was talking about anisotropy. That was my big thing, and now look at we're going to talk machine learning. I'm not going to even mention anisotropy here. Therefore, that's how people adapt to what's going on. A lot of what I'm going to present, of course, as usual, is my group work. I'm going to show most of it, but I have some slides at the beginning about my general thoughts about neural network that I like to share because it's interesting. There's a lot of debate, and what I put in here is one what do you call angle of what people might have seen in all of this implementation. As you could see, the title is talking about knowledge, and we will talk about that a little more. But before, let me acknowledge my group, the seismic wave analysis group. There might be a change soon. We're thinking about a consortium, me and my colleague Matteo Ravasi, who's a new assistant professor at KAUST, and we might have a different name. Actually, I'll say it is called Deep Wave, but we'll see how all of this. But for now, we're looking at seismic imaging, waveform inversion, and this is the new thing with the help of machine learning. And here is the list. And one thing you'll notice is ML is everywhere on this list. These are the people that are work on the group currently. And a picture of us. This was taken like a month ago. And you could see how sunny it is. That's what you expect from KAUST. This actually is the scope. And this was done, one of my previous students actually developed this with the help of some of his colleagues. He's now in Shearwaters. And it depicts what we're focused on from mostly in the exploration seismology level, microseismic, I'll show some of it in this talk, global as well, and we dealt with Princeton University on a very interesting project, as well as near surface. Therefore, we look at these things. But one of the things we noticed is there is this yearly NVIDIA KAUST Hackathon that is done at KAUST, and it's a competition between all the groups once a year, and our group won it 4 times out of the last 6 times it's presented. Actually, you could see one guy here that is that has won it for our group, and we thought, okay, if we did well with GPU, maybe we're good in machine learning. And we actually looked at it and start looking, not my idea. We're all driven by what our group wants, what our student wants, and they pushed us toward machine learning since 2016, and we've been looking at that topic and how it could help work with seismic. Therefore, my only contribution to this graph is I put a neural network in the middle to emphasize what we're looking at a little more. Okay, therefore the big question is, can we store knowledge in neural networks? And I don't have to explain neural networks a lot because Some of you might explain it even better than me, but just to be in the safe side, as you know, a neuron is where you take in inputs. Weighted summation is some mathematical formulas with some nonlinear, often nonlinear activation function, and you get an output y. The key thing here is this weighted summation, this W. Therefore, when you connect a lot of neurons, you'll have a lot of these weights. And these weights control what output you get, considering what input you may put. Therefore, what we're solving is an optimization problem in which we try to figure these W's that will give us the outputs over this training set. And this training set is made up of inputs and outputs if it's supervised, or it could be just inputs if we're, or inputs and the inputs in the outer side if it's self-supervised and there's many flavors. But after we train them, optimize it, that's the training procedure, we apply it to new data and we hope it will give us the answer or the prediction for whatever task we could look at. Therefore, we always have had data for anything, Earth, seismic data, gravity, there's a lot of data. And we have handled data differently over the years, since the beginning of the digital age. Therefore, at the beginning, we used to visualize data, use our experience and knowledge to do the predictions. After we could see these figures, we could say maybe this is something in particular, this is a reservoir, whatever we're trying to predict, or a horizon of a specific form. Later, recently, we've been using our knowledge to write codes. And these codes, usually called fixed algorithms, do the prediction. And this has been very prevalent the last 20 so years or more. Lately, we take the data, train the machine until it gains experience or knowledge, some people call it knowledge, to do the prediction. And we cut out the middleman or woman. Therefore, and that has been what, and then all the fad. Everybody got excited, even in science. Look at Nature, science, workshops, everything. This was launched, Nature Machine Intelligence. Actually, when they first launched it, there was like 3,000 signed a boycott from the computer science community against this journal because they didn't want to, they were charging. And I think it was not something they liked for publishing. And therefore, that was an issue. I don't know how it was resolved later, but there was everybody. And let me call everybody and their uncle was excited about this. But there was an issue of this. Therefore, it became a fad. And then this data scientist name became very, very attractive. And even I know geophysicists calling themselves now data scientists. I might do that because it brings attention. But look at this cartoon expresses some of the look at it. You have I don't know, I'm not going to say computer science are snakes, but computer science depicted as snake, tell the elephant, which is the statistics, teach me statistics, swallows the elephant and becomes a data scientist. And of course, the idea is it's all in the data. And knowledge can be stored or can be learned from the data, and maybe we don't need our physical models. And this trend became very popular in the last 5 years, and you got all of these articles. This is only a sample that are predicting the end of science, machine learning and the end of science. So you could go and read them, very easy. Just write the machine learning end of science, you get a lot of these interesting, data has a better idea, and so forth. Of course, in data science, cool titles are part of the fad there. And the idea here is that they are saying, maybe we don't need our knowledge. The only thing you need is data. Just teach your neural network It's agnostic to the physics, and we usually refer to it as a black box. And for some, it has resulted in better predictions than what we got from our formulas. Some cases. And that became an issue because that's how they decided to predict that maybe we don't need to understand what's going on, just predict. Therefore, there is this question. If we could predict without understanding, is that enough? For example, if you want to go and when they hypothesized that the outer core is fluid, that mainly came from our understanding of seismic wave propagation. But if you could get from the data or utilize the data to discover this without even knowing anything about seismic wave propagation, is that okay, or that's fine, or that's enough? And maybe we don't need knowledge and understanding the typical way. And it got really interesting. I mean, they lived in this very interesting world of knowledge in neural networks. To the point, I pulled this out. This is an example from a paper. And of course, one of these architectures is this teacher-student architecture, in which you have a teacher that is pre-trained to predict something. And as soon as it's pre-trained and learned, you allow it to predict on new data and use these predictions as the labels for the student. And according to many of these papers, the students will end up, if you could believe that, better than their teachers. And therefore, that's part of it. But look at the abstract with this paper. Recent years have witnessed dramatic improvements in knowledge distillation. Knowledge between these two neural networks, not between people. We found that the larger teacher model may be too overconfident. Thus, like the larger T, like a teacher with an ego, maybe, too overconfident that the student doesn't learn effectively. They're talking not about people, they're talking about neural networks. While after a simple model collaboration of the teacher, the size of the teacher model has a positive correlation with the student, and therefore the results look better. Therefore, the language is emphasized here really depicts that this is how the new thinking, that knowledge is in neural networks and it's carried in neural networks. Therefore, let me remind everybody what is the definition of science before it becomes obsolete with all of the predictions. Therefore, it's the enterprise that organizes knowledge and discoveries and observations. And it does it through libraries, through journals, through people, through institutions over the years. Therefore, that's the idea, this accumulation of science, and you can see how far it goes back. The question is, what is the goal of science? Yeah, some people will say the goal is predicting. That's where the value is. What about understanding? And how much does that add or remove? And this has been a full cycle, because if you go back to the early ages of discovery, it goes way back to Aristotle and but let's say Kepler from the mid previous century. Of course, he was very famous for predicting, for calculating data and predicting in terms of the trajectory of the planets and the moon and so forth. And he was actually practicing one of the first regression problems in trying to use data to predict where planets will end up being. Galileo did some of that until Isaac Newton and many others came and started to give us physical models, like force equals ma, mass multiplied by acceleration. And we didn't need data to try to predict, because now we could use our knowledge, physical knowledge about gravity, about the planets, and know where planets will go, not predict. Therefore, there is this full cycle. It's like we're heading back to predictive models again. We've gone from predictive models to physical, which is much easier, like Newton's second law, in which you could utilize it easily with other formulas to, if you send a rocket to the moon, you will know where its trajectory and how it will come back to Earth. And you didn't need to predict. And now they're saying, wow, we could go and do much more with predictive models because even our knowledge or our physical knowledge is limited. And hopefully we'll get. Therefore, let me just try to explain beyond the hype. What is ML, my view? Of course, everybody has their own view. It's a numerical tool, nothing more, nothing less. It's a very extensive numerical tool, and it's based on optimization. One of the key features in it, interpolation and extrapolation, is part of it, but it's not a regular interpolation. It's an optimized form of interpolation. Therefore, instead of relying on handcrafted transformations like the Fourier transform, within it, it develops its own transformations and basis functions that are optimized for the task and the data you utilize. Therefore, it's based on learned features, of course, and we will see examples of this that is very interesting. The most important thing to remember, it has a lot of limitations, and that's one of the key things we will talk about. Actually, here is an example of, if you extrapolate, this is one of my students, new students, and if you extrapolate between our pictures, simple pixel extrapolation will not do well. But if we try to input this as data and many pictures, it will learn the basis functions that is necessary to identify eyes, to identify nose, to identify, and this happens with all. It captures the features and uses that basis function for interpolation, and therefore you will end up with a much better interpolation. How about let's not get carried away with the machine learning. It has its problems. And here is an example. Of course, I extracted this from GPT-3 is a popular transformer network used for natural language processing. They have trained their huge GPT-3, and they're using it here for a simple, what they call suicide rescue line. Therefore, the man says, I feel bad, I want to kill myself. The GPT, I'm sorry to hear that. I can help you with that, maybe. Should I kill myself? I think you should. This is just testing for that aspect. Therefore, that would be a disaster. Of course, cars are still not driving itself. Therefore, we should go ahead.
Maybe it's doing the right thing. It's learning reverse psychology.
Okay, good point. Yeah, because if you tell him no, you never know. In psychology, you might say, okay. that might be. And of course, Google flu, which was a disaster after it started very well. 2011, it started to predict there's no science in it. They were using only data, nothing about transmission of the flu or anything related to that. And it started to overpredict by almost double the amount of flu expected. And they did it for many countries. And in 2015 or 16, they stopped it. Therefore, science and knowledge is still needed in machine learning. Here's a nice example of what is called adversarial attacks. It's very interesting. This is, for example, if you take a neural network model trained using the big MNIST data of figures or even bigger data, and it's trained to classify this as a duck, if you add very small 0.07 random, this is very smart perturbations that are extracted from the model by doing a back propagation with respect to the source to any other class, in this case force. This perturbation, this small perturbation, look at it, looks like a duck. That neural network will classify it as a horse. For that's a weakness. Even audio. How are you? This is what is written here. A small perturbation, 0.01 of that size. And this looks the same. And it will classify it as open the door. Therefore, that's an issue. And this has been is a big topic in machine learning, this adversarial attacks and how to work with it or solve it. And actually, there's some networks that are more immune to it, like transformers compared to CNNs, which is a big. Therefore, I extracted this from Carpetney and co-authors. They were talking about physics and machine learning, or science and machine learning, and what they are saying, it's not, we have knowledge gaps. We cannot solve everything with physical models. We definitely cannot solve everything with data because data has its own problems and errors. The solution is somewhere in the middle. And therefore, we ended up with something called, I called it this, but it has many names: physics-informed neural network, ML-assisted science and physics, because we have an optimization problem. When you have an optimization problem, you could induce or put in our knowledge of physics and prior knowledge of any form. Let me share you two examples, then I'll get into our examples of that. Therefore, this is, of course, Hamiltonian dynamics. Along came Hamiltonian neural network for a pendulum problem here, or mass spring problem, I'm sorry. And in this case, there's two ways to solve. You have the position and the momentum, and you could use a what I call a black box network to predict its evolution with time, which we do for anything, for ray tracing, for the motion of the moon around the, or motion of the Earth around the sun, or whatever. However, they noticed that if you do that and you try to train, there's no mass conservation here, and if you have errors in your data, you get errors in the prediction. A simple tweak in terms of inputting these and using the Hamiltonian, you could actually backpropagate and get the derivatives and use the Hamiltonian equations or the Hamiltonian Jacobi to predict the evolution. And in that case, you get a very accurate prediction. Not to be 1 year later, Cranmer and co-authors did the Lagrangian neural network. And in this case, they even wanted to outdo the previous paper, and they used the double pendulum problem. And this is what you observe in the double pendulum. That's a plot from it I got from Wikipedia. And in this case, instead of, again, doing just a blind neural where there's no conservation of energy, you get lost and you get inaccurate solution by inputting the position and its derivative. You could use the Lagrangian, use the backpropagation. This way you conserve energy, and you could actually compute the Lagrange-Euler equation from the Lagrangian without, therefore you're utilizing something that forces the conservation of energy, and you will get an accurate solution. Therefore, there's a bigger framework that has been introduced by Rossi and co-authors called physics-informed neural network. And in this case, you represent the neural network becomes, or you utilize it as a function. Therefore, it could be the wave field, it could be the travel time as a function of the input, x, a continuous representation. The only thing you need to do is make sure it satisfies the corresponding PDE. Therefore, it will end up learning to be a solution to a specific PDE. We utilize it for travel time, we utilize it for wave fields, and I'll show examples of that. Therefore, one of our first utilization, this goes back to 2019, is we actually, at the beginning, of course, this is a much newer, we would input in this network is a function of x, z, and the source location on the surface. Therefore, it's like a Green's function. The output is the scattered, real and imaginary part, because we're doing the frequency domain version. A lot of people are having problems with the time domain. It's not all solved in these pins, and they're trying to introduce causality and other things to help the training, but it's still a very tough problem. This one is much simpler. I'll show you why. And of course, using automatic differentiation, you get the derivatives, and you plug it in the Lippmann-Schwinger form of the Helmholtz equation. You could add boundary conditions, as well as, of course, in this case, since you have a background, we make the velocity constant for the background and get an analytical solution on the fly. And therefore, we solve for the scattered wave field. And that's what you see on the right. The training points are just random. And this is very nice because now you're flexible with the domain. And even if it has gaps for some reasons, you could still extrapolate or interpolate. And here is the results. The key thing, this is only 2 Hertz. And there's a problem. These neural networks, imagine this is a neural network representing a function. Therefore, if this function is complex, if these are complex like for high frequencies, it is not easy to train these neural networks to get, because there's a bias. There's a low frequency bias in neural network representations. Therefore, here we started with 2 Hertz, and it's a good approximation that we got through pin. The key element here is the pin size. We had only 2 hidden layers with 4 neurons each. We had a positional encoding because I could talk a little bit about it later, because it helped. It represents these inputs instead of in terms of a single scalar variable, it becomes a vector representation, and therefore locations become more sensitive. It's good when the function is isolatory. Therefore, 96 parameters. This is a 3-dimensional function representing this wave field. Only 96 parameters or coefficients is needed to. This is a big storage of such information. Imagine if you wanted to represent this on a regular grid, 3 dimensions, 100 by 100. Maybe if you're, 2 Hertz, maybe you could go down to 50 by 50. Then the sources is the 3rd dimension by 20. And you still have much bigger than 96 parameters to represent this wave field. Therefore, the basis functions hidden here really helped us reproduce this wave field very accurately. Therefore, because we really were worried about this low frequency, we actually observed the low frequency bias. Here's a function given by a summation of 2 sine functions, and we're represented by the input x, giving us this function sine, and we're trying to teach the neural network over epochs to learn it. This is the actual function. This is the frequency representation. And you can see it fits low frequencies much faster than it starts to fit, and it will never hardly fit the high frequency part. And this is a problem with neural net. It has this low frequency bias that many authors have pointed out too. Therefore, what we did, we said, okay, let us evolve our solution. We start at 2 Hertz, and after we teach it for 2 Hertz with a small network, we do something called neuron splitting. Use, like in FWI, use the initial values that learned here, the final values of the network learned here as initial for the second one. And the neuron splitting process is very simple to get the weights, corresponding weights for a larger network. Therefore, we would go from 2 Hertz to 4 Hertz to 8 Hertz and start to predict higher and higher frequency. And here is an example of 32 Hertz, which you cannot find in the literature. Therefore, this is the numerical solution, which is not cheap. And this is only for 1 source. This is our neural network for continuous sources. You could pick source on the surface any place because it's a function of 3 dimensions, including the source location. Here, the source was in the middle. And here is the difference. There is very minor difference plotted at the same scale. But overall, it predicted at 32 Hertz very accurately the frequency domain wave field. We said, okay, let's take it to a higher representation. This low dimensional. This is the whole idea of a neural network. It's a low dimensional or low dimensional representation or manifold of a higher dimensional like domain representation. Therefore, here is the GLAD at 24-kilometer depth, a plot of the GLAD M25 model. This model is administrated by Princeton University with the help of many scientists. And it's considered one of the good models of the Earth that they are evolving, or therefore this is the original model. We put it into a neural network where this function we're learning is the travel time from any source within that model area that is from the boundary of the outer core all the way to the Earth's surface or close to the Earth's surface to the receiver location. These are all inputs plus the velocity. And we use the iconal equation to teach the neural network. And we get the travel time you see on the right, an example of a source location travel time you see on the right. We could use the iconal equation to go back to the velocity model explicitly. And that's what you see on the upper right. And if you notice, it's very similar. Yes, it loses some of the high frequency features in some areas that you do not get smoother representation, which we expect from a neural network, but it's still a nice representation. This is a 6-dimensional function. And it stored travel time instantly from any source, not to any receiver. We trained it for the US array for now, and we have added more to than the US array. The training costs a lot, it costs a couple of days, but when you use it to get travel times, it's instant. And you could actually get the velocity instant. Therefore, it's a way to store the velocity model. At any depth, this is one depth, and of course, I could show you the accuracy of it over, this is a slice through the equator, and the left is the numerical or the input. It's the original velocity. On the right is the recovered. You don't see differences because the velocity is changing with depth a lot. And therefore, if we take the residual and blow it up by 100 times, you start to see some differences. But it's reasonably low differences. And then we started to use it to extrapolate. Therefore, here's an earthquake located, this one in Chile. And we trained with US array, but we said we want the travel time instantly along a line at some longitude. Therefore, here's as a function of latitude from 20 to 50, the travel time from the neural network, travel time calculated using the iconal, very close. But remember, this is instant. And the stars are pointing to the peak travel times from the stations. What's critical here is we trained only to the US array, but this line is expanded beyond the US array and is still extrapolated nicely the results of the travel time. And on the right is the errors involved at a closer, much focused level. Therefore, it's almost at zero. There's very little error. And of course, the peaks are scattered up and down because picking is not that accurate on the stations involved here. I knew, you know, errors in picking is a big issue. But it's scattered means we're right in the middle. We used this idea of pins to extrapolate seismic data. Therefore, we imagine this is a gap in the middle. Therefore, you have a gap here. You could easily use neural networks to try to predict in the middle without any PDE to constrain it. And this is what you get. If I use the plane wave destructor, which John Claerbout first proposed way back, and Sergey has used a lot or developed on it. If you use it as a PDE, you interpolate almost perfectly. You have to first calculate the slopes on the sides using PWD, then you could use both to constrain, and it will interpolate very nicely in the middle. Okay, this is pins. I'm going to go to a different form of storing information about seismic data. And this is based on a concept very popular in machine learning of pre-training self-supervised and then fine-tuning your network. And we're going to utilize BERT, which is the bidirectional encoder representation of transformer. Okay, it's a big name, but what it means is we're going to use the encoder part of a transformer, which is used for language. The inputs are words in a sentence. Transform to vectors, this is called word embedding. We're going to replace it by seismic traces. Therefore, this is a shot gather input, goes to a linear transformation. I'll show you what this linear transformation does. Through this network, the key feature of it is this multi-attention, multi-headed self-attention. It's like parallel attentions at many scales. I'll show you the scale issue. We use 4, and then you predict, and we try to match it to the same data. This is the pre-training. Here we mask 15%, and we measure the loss at the masked locations. You say this is interpolation. No, it is interpolation, but it's meant because the only part that communicates between these traces is the multi-headed attention, which is nothing but a weighted summation. It's trying to learn the geometrical features in the data by doing a weighted summation of filling the gaps. And when it does it, it stores these geometrical features inside. When we finish storing these geometrical features, we go ahead and fine-tune it for a specific task. And actually, we're developing this and advertising this as data set centric machine learning. Meaning, if you have a data set from the field, we're not going to build a machine learning model that does interpolation or does first arrival picking for many data. It never works, actually. For it to, because of the features of different data, it's very hard to adapt it to new data. Here we're saying, you have a data set, we're going to make it easy for you to store the features and then utilize it in many tasks. And we're going to show examples of these tasks: velocity estimation, low frequency prediction, which is very popular here, and other tasks. But we have one more feature in it. Since it has a pre-training self-supervised step, we could mix field data with synthetic data of the same. Of course, we do that all the time. We generate synthetic data. No, not all the time we generate for random models, but we generate it for FWI. We try to generate synthetic data that look like the real data. In this case, we generate using the same acquisition, using random models. We actually generate 3 shot gathers per model, and maybe 1,000 models, above 1,000 models. And this is real data. This is actually CGG data, offshore marine data. And we pre-train them together in this network. After we finish pre-training, we fine-tune with the synthetic, because field data labels are very expensive and they're often not there. That's what we want. Synthetic data, we actually model from the labels most of the time. And then we apply to field data at the end, after we train it for the various tasks. Therefore, here is an example of a field data and a synthetic data. We cut it to 3 parts because we're going to do low frequency prediction. We cut it to a part we call high frequency. High frequency, of course, for FWI type of things. 4 hertz, above 4 hertz. Then we cut to what we call low frequency, below 5 hertz, filter. And then below 2.5 hertz, we call it ultra low frequency. We're going to show that even the field data doesn't have this ultra low. We could predict something there. It's accurate or not, that requires another step. Therefore, here's the pre-training on both synthetic. This is an example. These are test data to show that it did well. It predicted the gaps with very minimal. There is some residual, but this is multiplied by 10 to emphasize, and they are weak. The training for this data took 12 hours to almost 13 hours. And here are some of the parameters of the training. We use a hidden dimension for each trace, 257. That means the original was 300 something, converted to 256. 4 layers and 4 attention heads. This is what it means, 4 attention blocks. sequentially. Here is one of the features that we like about this transformer. Therefore, you have an embedding layer. This is the input. It goes to a linear transformation here to a lower dimensional. Therefore, this is, I think, was 300 something, becomes 256. Each one, this is a common matrix applied to all of the traces. For every shot gather, we put one shot gather. Shot gather is like a sentence, and every trace is like a word in trying to relate it to natural language processing. Therefore, we put a lot of shot gathers. And this transformation, after training, after optimizing, looks like this. Therefore, this is the dimension, 370 of our inputs. The bottom here is the transformed. And if you look at it carefully, it's hard to see it here, but it's going from low to high frequency. And when we Fourier transform, you could see it. Therefore, part of the optimization, it learned that it needs to Fourier transform the data. This is almost like a Fourier transform. These are the basis functions for representing this, and these are the coefficients. And it's actually increasing in frequency as we go from left to right. Therefore, that's something learned inside the network. There's no Fourier transform. It learned that is good for seismic data. Therefore, here is 4 examples. We've done much more. Denoising, low frequency experiment, first arrival, velocity. Therefore, this is the fine tuning after we pre-train. Therefore, you pre-train, you store it. Now we want to use it for something. It takes only 3 hours to denoise, to fine tune it for compared to the 13 hours. And you could see here, this is multiplied by 10. We use the synthetic data to train, and then we apply it to real data. And you can see the backscattered energy in the real data, which was used in the training by propagating some of the information of the real data noise to the synthetic. Did the real well, multiplied by 10, you could see how clean compared to the original one, and removed a lot of these backscattered energy. Another one is low frequency extrapolation. Therefore, here's the synthetic input. No, this is the low frequency predicted original for the synthetic data, test data. And here is the result of the prediction. Not exact, at least this is nice. Here, the energy is much lower for the ultra low frequency. And if you look at the real data, inference, we don't have low frequency in the real data. We have some middle. You can see how much they match. And you could see after fine tuning, it actually got some energy at the ultra below 2.5 hertz, which is good for full waveform inversion. Another one is first arrival picking. In this case, it took only 7 minutes to train for first arrival picking, because your output is just a representation or a probability distribution of where is the first arrival. Therefore, this is a test synthetic example, and this is the field data example. And by doing this, we don't have only the first arrival pick, we have the distribution of how much confidence we have. And you could see at the near offset is almost perfect. As you go further away, you get a little bit of, the confidence gets less and less, which is expected as the wave complexity is a little higher. Okay. And here is predicting velocity. And again, this is the synthetic test. After we fine tune, it took 22 minutes to fine tune for velocity prediction for every shot gather. And we had a well for the real data. And here is an example of how the results came compared to the well. Therefore, the general trend is captured. It's not perfect, but there's another reason. This data that is from offshore Australia, there's a lot of anisotropy. The well, I said I'm not going to mention anisotropy, but but the well is the vertical velocity. What you get from seismic data is like the horizontal velocity or the NMO velocity. and that is usually higher, which can explain some of this increase caused by the seismic. Therefore, we didn't include anisotropy in this training. Okay, let's see how we're doing with time. Woo. Okay, I'm gonna go really fast through this part. I think I got really excited about this philosophy of knowledge. But here, one of the important things in machine learning, or the problem we face in machine learning, is when you train on synthetic data, how are we gonna generalize it to real data, to applicate? Because otherwise, in real data, you could utilize your previously picked horizons, you could utilize any information you've done, fault. But if you teach or you learn or you train a network on these picks, they will be as good as you're picking with these fixed algorithm, or you did it yourself manually. Therefore, synthetic data is very important because it represents, first, it represents the physics, and we need the physics. And secondly, it provides these labels for you depending on the physics you have assumed. Therefore, we developed a method for that. I will go through it fast because of the time. I didn't expect us. Therefore, this is microseismic, which I think should be exciting here a little more than what I presented previously. This is to monitor hydraulic fracturing. This is from the United States, Arkoma Basin, given to us by Seismic. It's a Czech company that does microseismic. And this is a plan view. On the right is a plan view of the sensors. It's made up like a star shape. And what you see over there are the wells as well, given by numbers 2, 4, 5, and 3. And these 10 arms are plotted here. This is an example of an event measured on the surface. It looks nice. This is a microseismic event. It's clean. However, we want to convert this to locations of the events. They gave us the velocity model, which is good, 3D velocity model. They gave us 75 locations. We couldn't use all of them. They weren't accurate, most of them, but there was 10 accurate. How did we decide which is accurate or not? We took the location, modeled from the location using that velocity model, and correlated the synthetic data with their real data, and the highest correlation ones were considered as accurate. Because otherwise, how could we, if we use inaccurate locations or inaccurate, we will have this problem with the reference they gave us. One of the things we promoted very early is when you have seismic data and you don't care about the time of the seismic event, only on the location, we could actually correlate with the reference trace. That will bring all of your events. Imagine you have recorded 1 hour or 1 day. All of these events, when you cross-correlate, will come to almost zero lag. They will be over each other, but there is zero lag. There will be a lot of crosstalk later, but we don't care. What we care is what ends up at this very small window. And this small window of, you can see here from minus 0.1 to 0.2, whatever events there, we could train the network on those. We do it on the synthetic, therefore we model so many data, and then we do it on the synthetic, and we will apply real data. Therefore, this is our network. I'm not going to spend a lot of time. The arms are input as channels into these convolutional layers. The output is the location of the data, of the microseismic event. We did even amplitude and frequency, but that's another story. Therefore, our training data comes all synthetic. We just put a point source, acoustic medium, and we model, and we get the data using the same configuration but of course, there's a problem to take this network from synthetic to real data, and we have a solution for that. Therefore, here's an example of synthetic. We actually generated 5,000 random sources from the region of interest, and we modeled from this 5,000. We have 5,000 synthetic. We used 4,000 for training, 1,000 for validation. But we went through a process. We call it ML real. Of course, we're doing what machine learning people do, use fancy acronyms. But the important thing is the content. Therefore, this is the real data. This is the synthetic. From a source, we know the source, therefore it's almost from the same source, but we didn't know the time. Therefore, they're shifted. What we did, secondly, we take a reference trace and cross-correlate one reference trace over the whole. And what will end up, they will all be converged to zero lag. This is a real, still very different. That's what we did previously. And we got reasonable results. But we added what we call real data noise here. There's a way to add it by taking segments of real and reproducing them. You could use GANs to do that as well, to produce real data noise and input it in the synthetic data. But here we promoted something called autocorrelation. We would autocorrelate both of these, then convolve, cross-convolve to produce our inference data and to produce our training data. Therefore, here's the autocorrelation. This is the synthetic and this is the real. Now we convolve, and this is the final data. This is our inference coming from the real, and this is the training. The key thing here is this, all these linear processes does not affect the phase. They're just migrating a statistics of the noise in both data to the other data. It's a mix of both data. They look very similar. Even the energy distribution are similar. But the most important thing is they have their own features embedded in them. Therefore, we went ahead and did the training. Here's the training loss for the locations. The total loss is in blue. For every one of these, Z, of course, has larger errors than X and Y, because from surface seismic recording, Z tends to be the hardest to really pin down. And you see it both in the validation and the training set. Now we apply it to the real data. And here is the results for 10 locations. This was our previous results, the one without autocorrelation, which is the black, which is the furthest one from the reference. The blue is the reference. And you could see that no, not the blue, the red. I'm not good with colors. The red is the reference, and it's close to our predicted with this new method. And actually, this is a plot of the error. This is not easy, but this is the plot of the error. Therefore, on the left is the label difference. This is our new result with ML real. The dash one is our old result. And you can see that the average error in location for real data is something like 20 meters or 15 meters, where before it was 40 meters, with all of this mixing of the data in our training. Okay, let me give you a couple of key takeaways. This is the end of the talk. There's no question, science and knowledge can help. These black box neural networks is not the way to go, for one. Storing the characteristics of data in your neural network will be very important, especially in self-supervised or pre-training method or processes. Size-based physical modeling for neural network, I think, will have a lot to do. We have to include our knowledge. We cannot throw it away, although some are suggesting that. And prediction and understanding are not the same. I don't know, you guys might have a different point of view about knowledge, but let me end with acknowledgement. This is actually one of my students used a GPT-3 that tried for vision implementation and cut my picture and extrapolate it. And this is what you get with the extrapolation. And he, his name is Abdullah, and he showed me these pictures, and he was laughing. And I was smiling a little bit just to keep him, but I was thinking myself, I say, let's see who smiles during your defense. but of course, all of it comes from my group, all of this push, these ideas, our interaction, and I want to thank them. I want to thank you guys for having me here, for Jindang, of course, for organizing, for Laurent, of course, for approving, and Nouri as well for his inspiration in this, and of course KAUST and you for being here. Thank you. Open to any questions.
Thank you, Tariq. Do we have questions from Zoom and the outside people?
I hope they're still with us.
Do you please unmute yourself and go ahead? Oh,
I have a number of questions. I'm just wondering whether to give them to you now, or maybe we start lunch and then we can.
Yeah, anytime, definitely.
Anybody from the group or Zoom? Thank you so much for the talk. This was very insightful in a variety of ways, from the philosophy to the excellent results.
Yeah, I don't know about the philosophy, but a lot of this I could have gotten to more about seismic store or the ML real. It's interesting. I hope it really gets the attention. Oh.
I guess I can maybe start with a question on this location determination example you gave at the end. Wondering what you think about, as I understand it, you use the given locations for the real events as reference for validation.
Yes.
And then you use simulations to synthetics for the training of the network. So I guess this brings up quite a few questions. One of them is, do you trust more your model, or do you trust more the reference that were given to you? That's number one.
Yeah, this is a very good question. Actually, the extended version of this talk really gets into this concept, because this concept is part of a big field in machine learning called domain adaptation. The idea is when you have a trained neural network on a data, how much could it generalize on other data, considering the other data might not be extracted from the same distribution of this data. And then there's all of these methods based on cycle GAN and GAN that tries to make this work. However, we had to make an assumption in all of these domain. One version of it called the covariate shift. It means that you have to assume your modeling is what represents the Earth. I mean, this conditional or likelihood of what comes out in the output, which is related to our modeling, from the input is representative of the Earth. And it could be not the true. Therefore, it could be there's anisotropy and we did acoustic. Therefore, that's a very important, but it's a requirement for this type of application. We consider that. Therefore, where the error could come from, there's many ways it could come. And one of them could be our modeling is inaccurate. But remember, they use the same modeling for their reference. Right. And they did tomography, they did travel time. They picked these and did travel time. This is seismic, and they got these reference locations. Therefore, at least we are in agreement in the modeling engine.
Because I'm wondering whether you're not kind of pitching two traditional conventional methods against one another, except yours is a neural network kind of reinterpretation of a conventional method, and you just kind of quote unquote just looking at the difference between two somewhat conventional methods.
I should be clear. When we said this is the reference, it doesn't mean it's the accurate.
Right.
Yeah, it means that we were using it to guide us a little bit. We're hoping it's the accurate version. But the beauty of this, something I did not mention here is its context of application. The idea here is when you train this neural network with this concept, we didn't need to pick a rival. The only thing we need, if you have a DAS network or you have geophones and you've been recording for a long time, you only have to take segments, like 1 hour, 2 hours, and you implement this cross correlation. You could have more than one event overlap, and the network is trained to map these segments that are long segments originally, but thanks to the cross correlation, all of it. And remember, all the crosstalk, not all the crosstalk, if the events are overlapping in reality, you'll have crosstalks in the zero, but most of the crosstalk, considering these events have some lag in time between them, are away from this box of focus, which is a small box. Therefore, now we do this. You could go to the network, you have this hour segments, cross correlate, you have this small box, you input it. And our what do you call it, promotion here, it becomes a real time location, because it's very fast in it after you train it. But that part needs to be studied more, because if you notice, everything we did is one event here. We did multi-events in a previous paper, but we haven't done it on real data.
I think we have a question from this.
Yes.
My turn?
Yeah.
Hi, Tariq. I really enjoyed your presentation, and I've been trying to think of a question to kind of connect the different parts of it. So I would say that the beginning of knowledge is to recognize ignorance. And I would say also, for any data set, you can estimate the uncertainty, say in the form of estimating the covariance, estimating the bias. And it's not easy at all. It's very numerically challenging for big data to have this uncertainty quantification. But I think, what is your view on the current ability of any kind of trained network to recognize the uncertainty and therefore not be overconfident? And if it is not overconfident, it will sort of announce its ignorance, and then there's the opportunity for knowledge to grow. Because I think that's the only way. If it always thinks it knows, it will never know.
Yeah, it's not the neural network that thinks it knows. We think it knows, and I think.
But you know what I mean. It's overconfidence in the prediction.
Yeah, I think it doesn't have. It's all in the data, training data, and if depending on the training data, it has, of course, as you mentioned, its bias in terms of it has a distribution related. There's many sources of errors, and Laurent mentioned one aspect of it is, where did you get this data? Therefore, the bias could be the modeling you use for the training. That's a source of bias. But if we have this knowledge already as part of our training, we could actually slightly take that into consideration and know that our network has this limitation. And we should always keep this in mind.
Do you think the network itself can sort of detect its own overconfidence? Is there a way to do that?
Yeah, there is these bias network training mechanisms where you actually formulate a latent space, and you understand how much, what you could call it, certainty you could have based on this distribution in the latent space. And there's this normalizing flows in which it's invertible, and therefore you could actually go from different distributions to understand more your certainty depending, or your distribution of the data.
Yeah, that seems key to me.
Huh?
I think that's key, that the network itself sort of knows when to be confident and when it really isn't, and tries to warn the user.
I agree. In the general form, and there's a whole I think group of people are working on this aspect of trying to really add this element to it. For us, we are also looking at uncertainty and trying to understand a little bit of it with respect to, therefore we want to add uncertainty quantification to many of, like this one in predicting the location, or like when we showed the first arrival picking, we had a distribution of where it could be. Therefore, these are something we want to work on, but it will. We're still working on those.
Great.
For now, I think everybody's just. You are absolutely right. This is a very important component, but everybody is now seeing how neural network works in seismic applications more than talking about its limitations and bounds.
Yeah. Thank you.
Oh, you're welcome. Yeah, this is a big issue. This
Took the question out of my mouth. I wanted to ask about uncertainty too. I think it's a
Yeah.
major issue.
Therefore, for example, we're promoting this. This is where we're promoting it big time, and many of the companies that we talked about are getting very excited about this StorSeismic. Therefore, it's data centric. It handles field data and synthetic, but it's data centric, meaning you do everything for a certain data set. The question is, the next thing we need to apply a mechanism of quantifying uncertainty in whatever inference or whatever, whatever fine tuning we do. And this fine tuning uncertainty could be propagated to the inference. Therefore, we do not only give an answer, we tell how much confidence we have in that answer. And this, we want to do it, actually. We're talking about it, and we want to do it for this because this is likely going to become our flagship for the next year or two as we try to find sponsors for the group. But this is a very important topic. There's no question about it.
Yeah. But if we don't have more questions, let's thank Tariq again, and we have lunch box outside.
Okay, great.
Thank you.
Thank you. How do the virtual people get the lunchbox? Can we?